This is the lecture for the second part of section 4.5, Irreducibility in Q bracket x. Now, given a polynomial f of x in Q bracket x, there exists a non-zero integer c such that c times f of x has integer coefficients. If c times f of x factors in z bracket x, then f of x factors in Q bracket x. Just divide the factorization in z bracket x through by c. Next, we want to show that if a polynomial with integer coefficients factors in Q bracket x, then it also factors in z bracket x. This result reduces the problem of testing polynomials for irreducibility in Q bracket x to polynomials with integer coefficients. Before we can prove this theorem, we first need a lemma. This is lemma 4.22. Let f of x, g of x, h of x be polynomials in z bracket x with f of x equal to g of x times h of x. If p is a prime that divides every coefficient of f of x, then either p divides every coefficient of g of x or p divides every coefficient of h of x. To prove this, we'll use a proof by contradiction. So suppose the result of the lemma is false. Then there exists polynomials f of x, g of x, and h of x in z bracket x with f of x equal to g of x, h of x, and a prime p that divides every coefficient of f of x, but does not divide at least one coefficient of g of x, and does not divide at least one coefficient of h of x. We then need to derive a contradiction. So let's start by writing out formulas for our three polynomials. F of x is a sub 0 plus a1x plus down to a sub k x to the k. G of x is b sub 0 plus b1x plus down to b sub m x to the m. And h of x is c sub 0 plus c1x down to c sub n x to the n. Let b sub r be the first coefficient of g of x that p does not divide. Now, by our hypothesis, we're supposing that p does not divide at least one coefficient of g of x, so there has to be a first coefficient that p does not divide. And similarly, we can let c sub t be the first coefficient of h of x that p does not divide. Then p divides b sub I for I equals 0, 1, up to r minus 1, but p does not divide b sub r. And p divides c sub j for j equals 0, 1, up to t minus 1, but p does not divide c sub t. And let's consider the coefficient a sub r plus t of f of x. Now, since f of x is equal to g of x times h of x, then we have a formula for the coefficients of f of x in terms of the coefficients of g of x, h of x, and h of x. So a sub r plus t is given by the expression shown. So it's the product of the coefficients of g of x and the sum of the products of coefficients of g of x and coefficients of h of x, where the subscripts add up to r plus t. And we're going to solve for b sub r c sub t, and we'll obtain b sub r c sub t is the expression shown. Then p divides a sub r plus t, since p divides every coefficient of f of x, and that's a coefficient of f of x. And since p divides b sub I for each I equal 0, 1, up through r minus 1, then p divides each term in the first set of brackets. And since p divides c sub j for each j equals 0, 1, up through t minus 1, then p divides each term in the second set of brackets. And since p divides each term on the right side of the equation, it then follows that p divides the left side, so p divides b sub r c sub t. And since p is a prime, this implies that p divides b sub r or p divides c sub t. But this contradicts our choice of b sub r and c sub t, since we assume that p did not divide either of these. And thus the result of the lemma is true. And we're going to use the lemma to prove our theorem 4.23. Let f of x be a polynomial with integer coefficients. then f of x factors as a product of polynomials of degrees m and n in q bracket x, if and only if f of x factors as a product of polynomials of degrees m and n in z bracket x. So the backward direction obviously holds. If the polynomial factors in z bracket x, then it factors in q bracket x with the same factors. To prove the forward direction, we'll suppose our hypothesis. Suppose f of x factors as a product of two polynomials g of x and h of x of degrees m and n in q bracket x respectively. Then f of x is equal to g of x times h of x. And there exist non-zero integers c and d such that c times g of x and d times h of x have integer coefficients. Let's just choose the least common denominator of the coefficients in g of x for c and the least common denominator of the coefficients in h of x for d. Then cd times f of x will be the product c times g of x times d times h of x. And this is a factorization in z bracket x. Each of the polynomials there has integer coefficients. And the degree of c times g of x will be the degree of g of x, which is m, and the degree of d times h of x will be the degree of h of x, which is n. Now let's suppose that p is a prime divisor of cd. Then cd is equal to pt for some integer t. Then p divides every coefficient of the polynomial cd times f of x. And then by the lemma, it follows that p divides every coefficient of one of the two polynomials on the right, so either cg of x or dh of x. And this gives us two cases. And we'll assume without loss of generality the first case holds. So the two proofs will be similar and we'll just prove one of the cases. So we're supposing that p divides every coefficient of cg of x. That tells us that cg of x will be p times k of x for some polynomial k of x in z bracket x, where the degree of k of x is equal to the degree of g of x, which is equal to m. Then pt times f of x is cd times f of x, since pt is cd. And that's equal to c times g of x times dh of x. And cg of x is now pk of x. And so now we have a common factor of p on the two ends of this equality. Canceling p from both ends, we'll obtain t times f of x on the left end is equal to k of x times dh of x on the right end. And this is again a factorization of polynomials in z bracket x. So all of the polynomials here, t f of x, k of x, and dh of x have integer coefficients, so belong to z bracket x. So starting from cd f of x equals cg of x dh of x, we now have a similar equation, but with the prime factor p canceled from both sides. We can repeat this procedure with each prime divisor of t, canceling it from both sides until every prime factor of cd has been canceled. And the result will be an equality of the form plus or minus f of x equal a of x times b of x for some polynomials a of x, b of x in z bracket x, with the same degrees as the original polynomials g of x and h of x, so the degree of a of x will be the degree of g of x, which is m, and the degree of b of x will be equal to the degree of h of x, which is n. This shows that f of x factors as a product of polynomials of degrees m and n in z bracket x. And this is the conclusion that we wanted to prove, so this proves the forward direction, so completes the proof of the theorem. As an example of how we can apply this theorem, we can show that the polynomial f of x equal x to the fourth minus 5x squared plus 1 is irreducible in q bracket x. We'll use a proof by contradiction. So suppose f of x is reducible in q bracket x. We then need to derive a contradiction. Now, since f of x is reducible, then it can be written as the product of two polynomials of lower degree. By the rational root test, the only possible rational roots of f of x are plus or minus 1, and it's straightforward to check that neither of these is a root. Therefore, f of x does not have any rational roots, so does not have any linear factors in Q bracket x. Therefore, f of x must factor as the product of two quadratic polynomials. And by theorem 4.23, it must factor as the product of two quadratic polynomials in Z bracket x. So this tells us that there exist polynomials px squared plus ax plus b and rx squared plus cx plus d in Z bracket x, so with integer coefficients, such that their product is equal to f of x, x to the fourth minus 5x squared plus 1. Now, since the x to the fourth coefficients must be equal, on the left, the x to the fourth coefficient is pr, on the right it's 1, so then pr is equal to 1, and since the coefficients are all integers, this implies that p is equal to r is equal to plus or minus 1. Now, by factoring out minus 1 from each factor, if necessary, we can go ahead and assume that both p and r equal to 1. And so then we obtain the equality x squared plus ax plus b times x squared plus cx plus d is equal to f of x. So we can basically assume that our two quadratic polynomials are monic. Now, multiplying the factors on the left side, we obtain x to the fourth plus the quantity a plus c x cubed plus the quantity ac plus b plus d x squared plus the quantity bc plus ad x plus bd is equal to x to the fourth minus 5x squared plus 1. Now, equating coefficients, we obtain this system of four equations. And so we now have a system of four equations in four variables, and we can set about solving it. From the first equation, we obtain c is equal to minus a. Substituting into the second equation, we obtain minus a squared plus b plus d is equal to minus 5, or a squared is equal to b plus d plus 5. Since bd is equal to 1 from one of our other equations, then either b is equal to d is equal to negative 1, or b is equal to d is equal to plus 1. This gives us two cases. For case 1, we'll suppose that b equals d equals minus 1. Then a squared is equal to minus 1 plus 5, which equals 3. And this results in a contradiction since a is an integer, and so a squared cannot be equal to 3. Case 2, we'll suppose that b is equal to d is equal to plus 1, and substituting, we obtain a squared is equal to 1 plus 5, which is 7. And this again results in a contradiction since, again, a is an integer. So our contradiction shows us that f of x is actually irreducible in Q bracket x. The next result provides a very efficient method for showing that certain polynomials are irreducible. So this is theorem 4.24, which is called Eisenstein's criterion. Let f of x be the polynomial shown with a non-constant polynomial with integer coefficients. If there is a prime p such that p divides each of a0, a1 up to a sub n minus 1, but p does not divide a sub n and p squared does not divide a sub 0, then f of x is irreducible in Q bracket x. So p divides all the coefficients except for the leading coefficient, and p squared does not divide the constant coefficient. To prove this, we'll use a proof by contradiction. So we'll suppose that there is a prime p such that p divides each of a0, a1 up to a sub n minus 1, but p does not divide a sub n and p squared does not divide a sub 0, but f of x is reducible in Q bracket x. We then need to derive a contradiction. Now, since f of x is reducible in Q bracket x, then by theorem 423 it can be factored in Z bracket x. So there exist polynomials g of x and h of x in Z bracket x such that f of x is equal to g of x, h of x, and we can write out what g of x and h of x are. G of x will be b0 plus b1x plus up to b sub r x to the r, and h of x will be c sub 0 plus c1x plus up to c sub s x to the s, where our coefficients b sub I and c sub j are integers for all I and j. Then the constant coefficient of f of x will be the product of the two constant coefficients for g of x and h of x, so a sub 0 equals b0, c0. And by our hypothesis, the prime p divides a sub 0, and since p is a prime, this implies that p divides b0 or p divides c0, and this gives us two cases. And we'll assume without loss of generality the first case holds, and the proof of the second case is similar. So we'll assume that p divides b0. Now since p squared does not divide a0, then it follows that p cannot divide c sub 0. The leading coefficient of f of x will be the product of the leading coefficients for g of x and h of x, so that tells us that a sub n is equal to b sub r times c sub s, and by our hypothesis p does not divide a sub n, which implies that p does not divide b sub r. Then p divides b0, the constant or first coefficient of g of x, but does not divide the leading or last coefficient b sub r. Now it may divide other coefficients between the first and last. So let's suppose that b sub k is the first coefficient not divisible by p. So that means that p divides b sub I for each I equals 0, 1, 2, up through k minus 1, but p does not divide b sub k. The kth coefficient of f of x is a sub k, and this is obtained by summing the products of the coefficients of g of x and h of x. So this is b sub 0, c sub k plus b1, c sub k minus 1, up to b sub k minus 1 c1 plus b sub k c0. Solving for the last term on the right, we obtain b sub k c sub 0 is the expression shown. And since p divides a sub k, and p divides b sub I for each I equals 0, 1, 2, up to k minus 1, then p divides each term on the right side of this equality. Therefore, p divides the left side, so p divides b sub k c0, and this implies p divides b sub k or p divides c sub 0. But we already said that neither b sub k nor c sub 0 is divisible by p, so this is a contradiction. And now that we've obtained a contradiction, this proves the theorem. Now, Eisenstein's criterion only works in very special cases, but it is very easy to apply when it does work. As an example, we can show that the polynomial f of x shown is irreducible in Q bracket x. And examining the polynomial, we see that the prime p equal 3 divides each of the coefficients in f of x except for the leading coefficient, and p squared equal 9 does not divide the constant coefficient. So Eisenstein's criterion implies that f of x is irreducible in Q bracket x. So we get the result with basically no work at all. Now there are obviously many polynomials to which we cannot apply Eisenstein's criterion. The next theorem provides another method to show that a polynomial is irreducible in Q bracket x. Let p be a positive prime. For each a in z sub p, we'll let bracket a denote the congruence class of a in z sub p. So this is our old notation from back in chapter 2. And let's let f of x be a polynomial a sub k x to the k plus down to a sub 1x plus a sub 0 be a polynomial with integer coefficients. We'll define f bar of x to be the polynomial obtained by replacing each coefficient a sub I with its congruence class bracket a sub I. For instance, if f of x is the polynomial 7x cubed plus 12x squared minus 5x plus 14, then in z sub phi bracket x, f bar of x will be the congruence class of 7x cubed plus the congruence class of 12x squared plus the congruence class of minus 5x plus the congruence class of 14. And since we're in Z sub 5, the congruence class of 7 equals the congruence class of 2, the congruence class of 12 equals the congruence class of 2, the congruence class of minus 5 is the congruence class of 0, and the congruence class of 14 is the congruence class of 4. So we obtain class of 2x cubed plus the class of 2x squared plus the class of 4. So for our theorem, we're going to use these reduced polynomials. This is theorem 425. And let f of x be the polynomial a sub k, x to the k, plus down to a1x plus a0, be a polynomial with integer coefficients, and let p be a prime that does not divide the leading coefficient a sub k. If f bar of x is irreducible in z sub p bracket x, then f of x is irreducible in q bracket x. To prove this, we'll use a proof by contrapositive. So we want to prove the contrapositive statement. So we'll suppose f of x is reducible in q bracket x. We then need to show that f bar of x is reducible in z sub p bracket x. Now, since f of x is reducible in q bracket x, then by theorem 423, there exist non-constant polynomials g of x and h of x in z bracket x, such that f of x is equal to the product g of x, h of x. And we can write out what g of x and h of x are. So g of x is b sub r x to the r plus down to b1x plus b0. And h of x is c sub s x to the s down to c1x plus c0. Then the leading coefficient a sub k of f of x will be the product of the leading coefficients of g of x and h of x. So a sub k is b sub r, c sub s. And since p does not divide a sub k, then p does not divide either b sub r, or does not divide b sub r, and p does not divide c sub s. This implies that the degree of the reduced polynomial g bar of x will be the same as the degree of g of x, and the degree of the reduced polynomial h bar of x will be the same as the degree of h of x. So both g bar of x and h bar of x are also non-constant polynomials in z sub p bracket x. Now it's straightforward to verify that f of x equal g of x, h of x implies a similar relation for the reduced polynomials. So f bar of x is equal to g bar of x times h bar of x. And it follows that f bar of x is reducible in z sub p bracket x as required. And this proves the contrapositive statement, which proves the theorem. Now, to apply the theorem, we want to choose a prime p that does not divide the leading coefficient of f of x. We then need to show that the reduced polynomial f bar of x is irreducible in z sub p bracket x. Since there are only a finite number of polynomials in z sub p bracket x of a given degree, it is always possible, in theory at least, to determine whether or not f bar of x is irreducible by examining all possible factors. Note, however, that if the reduced polynomial f bar of x turns out to be reducible in z sub p bracket x, then no conclusion can be drawn from the theorem. The original polynomial f of x may or may not be reducible in q bracket x. For an example, we want to show that f of x equal the polynomial shown is irreducible in q bracket x. So we'll reduce f of x using the prime p is equal to 2. Then f bar of x is the polynomial 1x to the fifth plus 1x squared plus 1. So the coefficient of x to the fourth is 8, and in z sub p, 8 will reduce to 0. The coefficient of x of f of x is 4, which in z sub 2 will reduce to 0. And we'll just write f bar of x without the bracket notation. So f bar of x is x to the fifth plus x squared plus 1. And we want to show that f bar of x is irreducible in z sub 2 bracket x. Now note that f bar of x has no roots in z sub 2, so has no linear factors. The only possible roots are either 0 or 1, and it's obvious that neither is a root. So this means the only way it can be factored is as the product of a quadratic and a cubic polynomial. Now the only quadratic polynomials in z sub 2 bracket x are x squared plus 1, x squared plus x, and x squared plus x plus 1. Now the first three of these quadratics all have linear factors. X squared is obviously x times x squared plus 1 is x plus 1 times x plus 1, and x squared plus x is x times x plus 1. So none of these can be factors of f bar of x, since we've already said that f bar of x has no linear factors. So the only possible quadratic factor will be the fourth one, x squared plus x plus 1, and using long division we can show that this polynomial is not a factor of f bar of x. And therefore f bar of x has no quadratic factors. And this tells us that f bar of x must be irreducible in z sub 2 bracket x, and by the theorem we can conclude that f of x is irreducible in q bracket x.